We've looked at how functions are particular kinds of relations, and relations have domains. That is the collection of all possible inputs to the relation that you could get. Now, properly speaking, the domain of a relation is an inherent piece of information about that relation. However, we typically talk about functions in terms of formulas, and when we do that, determining the domain is not as immediately obvious as when we're looking at, say, a collection of numbers. And so we're going to talk today about how we can look at a function defined by a formula and determine its domain, that is the set of all possible inputs to that function. And then we're going to look at a couple of applications of functions. So let's take an example. Let's let f of x equal x over x minus 2. Find the domain of this function. Now, I want to take a second and remind us of what this notation that I've written down actually means. Let f of x equal x over x minus 2. We are going to be developing intuition about functions pretty quickly, but it is important for us to have the proper foundations here. So let's remember what this expression here really means. This means that f is the collection of pairs given by x comma y, where y equals x over x minus 2, and x is a real number. Now, I should mention that the restriction of x being a real number is one that we are often going to make in this course, but is not one that we always have to. In mathematics, we consider functions whose inputs can be all sorts of things. In particular, we've already looked at complex numbers, and complex numbers are definitely the types of things that could go into functions. We could have a function that takes complex numbers as inputs. Similarly, we can consider functions that only take integers as inputs, or sometimes only positive integers. Functions can have different sorts of classes of numbers that they work with. For us, by default, our functions are going to have inputs that come from the real numbers, but in other contexts, other courses, this might be very different. So make sure if you're ever unclear about what sort of numbers a function takes as an input, that you clarify that somehow. As I said, for us, the default is going to be that our variables stand for real numbers. All right, so f is the collection of all pairs x, y, where y equals x over x minus 2. So now the domain of f is the set of all x such that there exists a pair x, y in f. Now, if this pair xy exists in f, then we know that happens exactly when y equals x over x minus 2. So as long as we can describe this y right here, then we will be able to construct a pair. So for instance, if x is equal to 0, then we would get y equals 0 over 0 minus 2, which is 0 over negative 2, which is 0. So that means that f of 0 is 0, which means that 0 is in the domain. And similarly, if x is 1, then we could look at the y value 1 over 1 minus 2, which gives us 1 over negative 1, which is negative 1. So that tells us that if x is 1, y is negative 1 in this function. which means that 1 is in the domain. So we could look at this and say, all right, well, what could go wrong? What isn't in the domain? Because it seems like we can pretty much always come up with this y. We've got the formula. Isn't it the case that for every x, we just plug it into this formula and get a y out of it? And in some cases, the answer is yes, but in other cases, we have to be more careful. In this problem, for instance, there is exactly one number that we can't plug into the function and get an output. And that has to do with the fact that we have a denominator right here. And remember that any expression with a 0 in the denominator is undefined. So let's get a new page. We're looking at this function, f of x equals x over x minus 2. Now, what if we try to ask, what is f of 2? Well, we would try plugging 2 in. We would try evaluating this function at 2, and we would write 2 over 2 minus 2. So here we've plugged in 2 for x, and we've plugged in 2 for x, and gotten our expression. Well, that'll give us 2 over 0, which is undefined. Now, it's very important here that undefined is not a number. Undefined is not a valid thing that can go into a second entry of a function. So 2 comma undefined doesn't make sense. So there is no real number y such that 2 comma y is in f. Because if one existed, then y would have to equal 2 over 0. And that's simply not a real number. So this shows us that the number 2 is not in the domain of f. Now, 2 is not in the domain of f, but every other real number is. The only thing that can sort of go wrong with this expression, the only way we could make this expression not give us a number when we go to simplify it, is for the denominator to wind up being 0. And so if x is any other number, we're fine. If x is bigger than 2, then the denominator will be positive, which is fine. We can divide by any positive number. If x is less than 2, the denominator will be negative, but that's fine. We can divide by any negative number. The only number we're not allowed to divide by is 2. So 2 is not in the domain of f. So that means that the domain of f is, now there are a few ways that we can write this down. One way is using a number line, similarly to how we did for inequalities. And we want to include now the domain consists of all numbers, all real numbers other than 2. So it's going to consist of all numbers greater than 2 and all numbers less than 2, but not actually equal to 2. So we can sketch out the domain this way. We can also write it down using interval notation. So in this case, the domain of f is a union of two intervals from -infinity to 2 and from 2 to infinity. So this set, this union of two intervals here includes all real numbers except 2. And we could also write down the answer using set builder notation. We could say that the domain of f is all x's such that x is not equal to 2. So So these are just three different ways of writing down the domain of f. So remember that the domain of a function is the set of all points that you can plug into the function and actually get a number out of it. Let me write that down because that is really the best intuitive way of remembering what a domain is in the context of a function defined by a formula like we usually use. So the domain of f is the set of all numbers we can plug into f rather, and get an answer out of. So let's take another example. This one's going to be a little bit simpler. Let's look at f of x, which is defined to be 3x squared minus 2x plus 1. And we ask, what's the domain of f? So in the previous example, we had to be careful because we had a denominator, which could sometimes be 0 if we happen to plug in the wrong number into it. We don't have that here. We don't have any denominators. We don't have any way to make a denominator 0 by changing the value of x that we plug into this function. In fact, if we look at all the things that are happening to x in this function, x is being raised to a power, is being squared. We can do that with any real number we like. We can square any real number. It's being multiplied by other numbers. We know that we can multiply any two numbers together and get a number out of it. No problems there. It's not like division. And then we're adding and subtracting things. But we know that if we take any collection of real numbers and add and subtract them together, then we're going to still get a real number out of it. So in other words, there's nothing that can go wrong here. No matter what number we pick, whether it's 0, whether it's a billion, or whether it's some weird fraction, we're always going to be able to plug that into this formula and get a number out of it. So the domain of this function f is all real numbers, since we can plug any number into the formula 3x squared minus 2x plus 1 and get a number back. So the domain of f is all real numbers. We will usually express this set as the interval from negative infinity to infinity. So this is the set of all real numbers. It has no lower bound, it has no upper bound, it includes everything on the real number line. You'll also occasionally see the following symbol, this fancy capital R with the double vertical line. This is also just a symbol, mathematical symbol for the set of all real numbers. Usually, however, we use the interval notation to describe the domain because it carries everything that we need in it. All right, let's see some more functions with their domains. We've seen that fractions can be a problem. Let's look at another example with a fraction in it and see how we can deal with it. What is the domain of f of x equals x squared plus 3x plus 5 over x squared minus 6x plus 8? So this function's more complicated. Let's pay close attention to what the problem is asking, because there are lots of things that we might do with this function. A problem might give you this function and say, evaluate this function, plug these numbers into this function, tell me things about it. In this case, the problem's asking for us to find the domain. And the question we need to ask whenever we run into a problem asking us for the domain is we want to ask, what could go wrong? In general, if we operate on two numbers, if we add them, subtract them, or multiply them, or divide them, most of the time we get a real number back. What can go wrong is when we do things like divide by 0. And that's what can go wrong here. So we want to be on the lookout for denominators. Because denominators cannot be 0. If a denominator turns out to be 0 anywhere in the formula, then the whole function is undefined when you plug that number in, and therefore that number is not part of the domain of that function. So, looking at this function, we have a denominator down here, x squared minus 6x plus 8. We also have the numerator, x squared plus 3x plus 5, but we actually don't care about that. The numerator of a fraction can be anything that you like. It can be 0, positive, negative, and none of that is going to affect whether or not you get a real number out of the formula when you plug a number in. The denominator, on the other hand, will. We need to make sure that this denominator is not equal to 0. So our domain is not going to include any numbers that make this denominator equal to 0. How do we find these numbers? By setting the denominator equal to 0 and seeing what would cause us problems. So, to find the elements, or to find the numbers, let me be more precise. To find the numbers that are not in the domain, set the denominator equal to 0. And solve. What we will be doing there is we'll be finding all of the numbers that would make the denominator 0 if we were to plug them in. And therefore, we can make sure not to include them when we write down our domain, because our domain will not include those two numbers. So from here, once you get to this point where you've set the denominator equal to 0, for a few minutes we can completely ignore everything else in the problem. We can ignore why we care about whether this is equal to 0, ignore the numerator from before, ignore even the fact that there's a function involved. We're just trying to solve this equation. So we can think back to how we solve quadratic equations. And in this case, we see that, oh, we've already got a 0 on one side. That's great. Can we factor this? In this case, it turns out, we can. If we couldn't, then we would use the Pythagorean theorem. The quadratic formula. But in this case, this polynomial on the left factors as x minus 4 times x minus 2. And therefore, x minus 4 equals 0, or x minus 2 equals 0 by the zero factor theorem. And adding 4 to both sides of this equation gets us x equals 4. Adding 2 to both sides of this equation gives us x equals 2. So we get x equals 4 or x equals 2. So the conclusion that we draw from this is that if x equals 4 or x equals 2, the denominator is 0, which means that the function is undefined. So that means that 2 and 4 are not in the domain. To express our answer in interval notation, again, it's helpful to sketch out a number line of the situation. We have 2 and we have 4, and we want to include all numbers other than 2 and 4. So we include all numbers to the left of 2, all numbers to the right of 4, and all numbers in between 2 and 4. And we just want to eliminate the number 2 and the number 4 from our list. So our answer is the interval from -infinity to 2, union with the interval from 2 to 4, union with the interval from 4 to infinity. Or we could look at the set builder notation and say it's the set of all x's such that x is not equal to 2 and x is not equal to 4. So here's an example of how we look at the domain of the function. Once again, I want to emphasize that the numerator of this function didn't make a difference in the slightest. And we could have changed that numerator to almost anything in the world, and it wouldn't have made any difference. So there are two big things that we look for when working out the domain of a function. The first is denominators, as we saw here and in the previous example. We can't let denominators be 0. So the way that we work that out is we take the denominator, set it equal to 0, solve that, and then whatever solutions we get out of that equation have to be removed from the real numbers in order to give us our domain. The other type of function that we need to worry about when looking at the domain of a function are square roots, or more generally, any even root, so square root, fourth root, sixth root, etc. So for that, let's recall the following. The nth root of, we'll say a, is undefined if n is even and a is negative. So we often express this as we can't take the square root of a negative number. Well, we also can't take the fourth root or the sixth root or the eighth root or any other. However, the cube root, we can take the cube root of any number. So the third root or fifth root or seventh root or ninth root, etc. So the other type of function that we need to look out for when working with domains of functions are even roots. So we need to be on the lookout for even roots. So let's take an example. Let's let g of x be the square root of 3x minus 18. And we want to find the domain of g. So for problems involving roots, even roots, we're not going to solve for the bad stuff the way that we do with denominators. We're going to solve for the good stuff. We're going to solve for the x's that are in the domain, that do make the function defined. So note that g is defined if the stuff inside the square root is greater than or equal to 0. We can take the square root of a positive number, we can take the square root of 0, but we can't take the square root of a negative number. So what we want to do is we want to set the inside of the square root to be greater than or equal to 0, and then solve using our standard solutions to inequalities. So for us, what that means is that to find the x values that you could plug into G to get a number, that is its domain, we're going to take the stuff that sits inside the radical, inside the square root, 3x minus 18, and we're going to set it greater than or equal to 0. And now we're just going to solve. So we'll add 18 to both sides, get 3x is greater than or equal to 18, divide both sides by 3, and get x is greater than or equal to 6. So what this is telling us is that if x is greater than or equal to 6, then 3x minus 18 is non-negative, which means the square root of 3x minus 18 gives us a number. And if x is less than 6, then 3x minus 18 will not be greater than or equal to 0. It'll be less than 0, and so then we'd be trying to take the square root of a negative number, which doesn't work, doesn't give us a number out of it. So this means that the domain of G is, we'll start with set builder notation this time. It's the set of all x such that x is greater than or equal to 6. We could also sketch this out on a number line, but we can also just write it using interval notation. It's the set of all numbers from 6 to infinity. Note now that we're using the square bracket because we need this to be greater than or equal to 6, and that gives us the full domain of G. The last thing that we need to talk about is what happens when you've got more than one of these going on. What happens if you've got a function that has both radicals, both square roots or fourth roots or sixth roots or whatever, and fractions? Or maybe it has two fractions, or maybe it has more than one square root. And the answer is, in order for the function to be defined, every single one of its parts has to be defined. If any one of them goes wrong, if you've got a 0 in any denominator, the whole thing collapses. If you've got a negative inside any even root, the whole thing collapses. So you need to make sure that all of the parts of the function are defined and get a number out of it at the same time in order for a number to be in the domain of that function. Let's see an example of how that works. Let's find the domain of h of x, which is given as the square root of 4 minus 3x over x. Oh, I'm sorry. This needs to be plus of 3x. We want to find the domain of h of x, which is the square root of 4 plus 3x over x. So in this case, there are two parts to this problem that could give us issues. We have both a square root and we have a fraction at the same time. To find the domain, we want to handle each piece individually, figure out what each of them say about our domain, and then combine those two pieces of information together. So let's do the radical first. So for the square root, we need 4 plus 3x to be greater than or equal to 0. In order for x to be an element of the domain of h, this inequality needs to hold. 4 plus 3x needs to be greater than or equal to 0. Solving that for x, we get 3x is greater than or equal to negative 4, divide by 3, and we get x is greater than or equal to negative 4/3. All right, so as long as x is greater than or equal to negative 4/3, we have that the radical up above is defined. It gives us some real number out of it. But now let's look at the denominator. The denominator can't be equal to 0. So we have that x cannot be equal to 0 because x is in the denominator, and so if x were equal to 0, then the denominator of this function would be 0, the whole thing would be undefined. So when we look for the domain of the whole function, both of these must be true at the same time. We need an AND relationship between these two conditions. So our denominator is going to consist of all numbers that are greater than or equal to negative 4/3 and not equal to 0 at the same time. So let's sketch out what that looks like and then write down our answer using interval notation. So we want all numbers that are greater than or equal to negative 4/3. So we're going to get a square bracket there at negative 4/3, but not equal to 0, which means that we're going to remove 0 from that interval. So our domain in interval notation could be written as the interval from negative 4/3 to 0 union the interval from 0 to infinity. Because both of those conditions need to be true at the same time in order for x to be in the domain, in order for h of x to be defined. All right, so that's how we can determine the domain of a function. Now, there are lots of different ways that a function can be combined with or can be defined using combinations of fractions and radicals. And we're even going to see later on in the course that there are other types of functions that we'll deal with where we have to worry about its domain. More conditions to look at. For now, the only ones we have to worry about are the denominator, making sure that none of the denominators that appear anywhere in the formula are 0, and making sure that anything under an even radical, square root, fourth root, sixth root, etc., has to be greater than or equal to 0. To find the domain means to find all the numbers that satisfy both of those conditions at the same time. So now let's move and talk about some applications of functions. And we're going to look at a couple of them. We're going to look at one that's more abstract and is relevant in the development of calculus. And we're going to look at how we deal with real life problems and express those problems using functions. So let's look at one sort of abstract application, and that's called the difference quotient. So given a function f, the difference quotient, of f is defined to be f of x plus h minus f of x over h. Now here, x and h are both variables. So this is a little bit of an odd expression here. It turns out that this is the sort of expression that you might use to calculate the average speed of an object If you look at its starting position and its ending position, take the difference of those two and then divide by the amount of time it took for an object to go from one to the next, then that will give you the average speed. Well, it turns out that that's basically what's going on here in the difference quotient. Let's take an example and let's let f of x be x squared minus 3. Find the difference quotient of f. So the hardest thing about this problem is making sure that you are plugging things in properly and simplifying properly. And really, most of the difficulty comes down to this term right here, the f of x plus h. So let's do that down below. And the thing to remember is that when you take a function and evaluate it, then whatever is inside here is the input. In particular, it's one solid thing. And when you are going to plug your input into your function, that whole thing comes along all at the same time. So if my input is x plus h here, then that's exactly what I'm going to plug in to my function. Now looking back at my function, what you want to do is you want to see, all right, in the original definition, the input to my function was x, and then some x's show up in the definition, in the description of the function using the formula over on the right. So when I take f of x plus h, what I want to do is make sure that I replace each one of the x's in the original formula with the expression that I've put into the function down here. Whatever's inside the parentheses, no matter how complicated it is, takes the place of this x term right here. So f of x plus h gives us x plus h squared minus 3. So I just took my x and replaced it with x plus h. And that's all that it is. I think one of the things that makes this complicated is that people expect this to be more complicated than it is. People expect that, oh, if I take f of x plus h, then that means that I need to add something onto the end of things, or I need to take f twice and add it together, stuff like this. None of that is the case. Whatever is inside those parentheses in the function notation, f of x plus h, that whole x plus h simply gets plugged into the original function wherever x was before. And the fact that we're using the same symbol both in the x both in the definition of the function and in the input to my new function, f of x plus h here, that makes no difference at all. The x's that we use in the functions are, properly speaking, dummy variables. We could use other variables to do these things, and we'll actually see that in a second when we move on to our other applications. So let's finish this example here and then do another application. So f of x plus h is exactly what we get when we plug x plus h into the formula for the original function in place of x. Now, f of x, well, that's what we get when we plug x in place of x in the original function. So, in other words, it's just going to give the normal function back. So, f of x is x squared minus 3. And then h is just h down here. Now from here we can simplify things a bit And let's see, we'll get x squared plus 2xh minus 3 minus x squared minus 3. Sorry about this. About getting cramped down here. And when we distribute the negatives through, on the right, then we'll see that we actually have some cancellation here. We've got an x squared and a minus x squared. We've got a minus 3 and a plus 3. And so we're left with 2xh over h, which we can even cancel now the h's from the top and bottom. So in fact, the difference quotient for this function is simply 2x. So this is an example of how we might use function notation to define something like a difference quotient and then use that as we compute things. Now, if you go on and do problems involving difference quotients, do note that usually you will have some h's left over in your problem. In this case, all of our h's canceled away. That's usually not the case. Usually there are some h's left over. So if you're doing problems and that happens, don't be surprised. That's fairly typical. Okay, so let's do an application problem, more real-world problem. Right, so the cost to ship an item across the country is $30 per pound plus $56 in administration cost. Write a function C that gives the cost to ship an item of weight W pounds, then find the cost to ship a 12-pound item. So for this problem, we are being told to use different symbols than we were before. Before, we were using f's and x's, or sometimes g's or h's for our function. Here, we're being told to use different variables. We're told to use c as the name of the function and w for the weight of the item. So in this case, the problem has told us to use the cost as the function, but that also makes sense in the thinking about things in terms of dependent and independent variables. Typically, when I go to ship an item, I know the weight of that item is already fixed. I go in and I say, okay, I've got a 12-pound item. How much is it going to cost to ship this? And so the cost depends intuitively on the weight of my item. I don't typically walk into some place and say, oh, hey, I've got $100 to spend. How big an item can I ship? That's usually not how it goes. And so it makes the most sense in the context of what we're familiar with to use weight, the weight of the item, as the independent variable, the thing that changes on its own, or has its own value. And then the cost is the dependent variable. The cost depends on W. And we want to say, for an input weight W, what is the output cost? So we ask, for a weight W, what is the cost to ship the item? So the problem gives us information here. It tells us that the cost is $30 per pound plus $56 in administration cost. So if we're shipping a weight W item, let's get an expression that tells us how much this is going to cost. So the answer to this question right here is going to be the following. So we're going to take our $30, which is our cost per pound, times our W, times the number of pounds that our item weighs. And a lot of times the easiest way to make sure that what you've got makes sense is to think of it for certain specific cases. So ignoring the $56 in administration costs for the moment, we'll handle that in a second. We can, and just considering the variable costs, we can say, all right, so if it costs $30 per pound, if I had a 2-pound item, that would cost $60. If I had a 3-pound item, that'd be $90. If I had a 4-pound item, that'd be $120. And so I'm saying, all right, what operation am I doing there? What am I doing with 30 and 2, 3, and 4 in each of those cases? Well, I'm multiplying them. So if my cost is $30 per pound, and I'm shipping an item weighing W pounds, then that part of the cost will have a value of 30W. So 30W is the sort of variable cost of shipping, and then plus 56, which is sort of the fixed cost, the administrative cost. So the total cost for shipping an item with weight W is 30W plus 56. So, in other words, our functions in our function C, an input of W has an output of 30W plus 56. In other words, C of W equals 30W plus 56. That's exactly what this notation, this function notation down here means. If our input is W, our output is 30W plus 36. So that's the input that matches, or this is the output rather, that matches with that input. So that's an example of how we would construct a function that describes a certain real-world scenario that we're looking at. Let me get another page as we handle the next part of the problem. So next we ask, how much does it cost to ship a 12-pound item? So we know that the cost for a weight of W pounds is 36W plus 56. So when we ask how much does it cost to ship a 12-pound item, we're asking what is the cost associated with a weight of 12 pounds? What is the output corresponding to an input of 12 pounds? This is a relation where we can put in a weight and out of the relation should pop a cost. And we have the formula, so therefore, oh, I'm sorry, I wrote 36 here for some reason. should be 30. So C of 12 should be 30 times 12 plus 56. And so we can work this out. This is 360 plus 56, so 416. So the answer is that it costs $416 to ship a 12-pound item. And that finishes up the problem. If I wanted to know the cost to ship a 20-pound item, I would plug 20 into this function and find C of 20, or C of 17 for a 17-pound item, or anything else that I liked. As a little bonus that wasn't in the original problem, let's ask, what is the domain of C? Well, let's look at that this way. We got C of W is 30W plus 56. Now, from a purely mathematical standpoint, which is where we want to start here, we can look at this formula, 30W plus 56, and say, all right, well, what could go wrong? Are there fractions whose denominators could turn out to be 0? Are there square roots whose insides could turn out to be negative? And in this case, the answer to both of those is no. There are none of those. From a purely mathematically perspective, we could take any real number W we like, plug it into this formula, and get a real number out of it. So from a mathematical point of view, pure mathematical point of view, there's no restrictions on this domain. However, we're not in a realm of pure mathematics here because we're dealing with a real-world problem. And in a real-world problem, there are other considerations to work with. So, for instance, when we want to say what are the valid values for W, we probably are not going to include negative numbers. Negative weights typically don't make sense in the context of shipping items from one place to another. Now, let's ignore for a second the possibility of trying to ship sufficiently many balloons that your box is actually weightless. If that happened, then it would just float right off the truck. So let's ignore weird situations like buoyancy, like that. Let's imagine that that nothing's lighter than air, and in that sort of case, the weight that is measured for whatever you're shipping certainly can't be negative. Certainly, if you go into a shipping store and say, how much does this weigh, they're never going to tell you a negative answer out of that. And so, from the context of the problem, W has to be greater than or equal to 0. Now, we can have a discussion about whether this should really be greater than or equal to 0 or just strictly greater than 0, because it's a question about whether they would even consider shipping something that registered no weight on their scales, but they might. So a 0 weight might make sense, but a negative weight certainly doesn't. So for the context of the problem, W is greater than or equal to 0. So in this case, the domain of C, because it's based on this real-world problem where the input doesn't make sense as a negative number, the domain is actually going to be the interval from 0 to infinity and not including any of the negative numbers. We've talked about this earlier about how when doing application problems, many times your variables won't make sense as negative numbers, but sometimes they will. So make sure that you are looking at your precise contexts. Masses and distances aren't negative, but um, but temperatures might be, bank accounts might be. So there are some things that might be negative. So make sure that you're using your critical thinking and thinking about each situation on its own merits as it comes up.